Okay, good morning. Let's begin our lecture. A reminder, you're going to have the discussion section about counting today. I hope you enjoy it. Now, please make sure, I believe the discussion today is pretty short compared to what you got in the last couple of times. However, please use the discussion time wisely. This is your opportunity if you didn't do some of the questions in the last discussion or still have questions about last discussion. This is going to be your opportunity to ask your TAs to help you with them and maybe solve some of those questions from the discussion on the board. Induction proofs and the whole induction aspect is going to be extremely important both for this class and from next classes. So please make sure that, if you still have questions about it, make sure to ask them. Now, today we are going to continue and talk about counting. And let me start sharing my screen. So, any questions before I move on? Okay, I don't see any questions, so we will continue. So we are in section 6.2. We're kind of finalizing it, and I want to kind of remind you the general pigeonhole principle. It says that if you have n objects and they're placed in k boxes with n bigger than k, then there is at least one box with n over k objects. Now, so here is the question. How I'm going to give you a couple of exercises, and this time I anticipate you to give me the answer. Example. Oh, wrong color. How many people should I have in room to make sure at least 2 are born in the same month? So I'm strange, I'm trying to make a party, I want to make sure at least 2 people share the same month of the birthday. How many people I should invite to make sure, 100% sure that at least 2 have the same birthday? Yes, I see it in the chat. The correct answer is 13, because my first 12 people I invite might be of a different birthday, so we need to be like 13. I need to have 13 guests. Okay, what will happen if I want them to share the same day? Yes, it is just the same day. It's supposed to be 32 because some months have 31, correct? So maybe that's what I got. What about same day and months? Yes, it's 367 because some have 366 days. Okay, lovely. Here is one more. Come on. Here we go. So assume in my class, I might have we might have freshmen, sophomores, and juniors. And assume I need at least 3 freshmen or 19 sophomore or 5 junior. Okay. So question, how many students do we need? Well, let's see. This is where you kind of try to get a worst case scenario. I'm picking my class and I'm always missing it. So assume I take 2 freshmen. Can I do it? Yes. The condition is still not met, right? But now get was no freshman wants to come to my class. So I'll start and I'm trying to get my juniors. So I'm trying to get juniors and I'm lucky I got 4, but guess what? Nobody else is coming to me. And then I'm not lucky again. I'm getting 18 sophomores. So this is the case where I'm getting almost everything, but nothing I really want from my condition. So this is actually 24, correct? Agreed? So if I have 25 students, I have at least 3 freshmen or 19 sophomore or 5 junior. Now, this time I went with this question backwards with you. So because the student number 25 is either going to be freshman, sophomore, or junior. So either I'm going to have 90 sophomore or 5 junior or 3 freshmen, correct? So at this point, I'm going to reach this condition. So I went a little bit backwards to you to explain how this idea works. However, generally, it goes backwards. Generally, my question is going to have a question like this. Assume I have 25 students in my class that only consists of freshman, sophomore, and junior. Prove I have at least 9 of either freshman, senior, or junior. How do you prove me something like this? Of course, this question makes much more sense than my previous one, correct? In the previous case, we kind of went in a strange, the question was phrased really, really strangely, correct? But this one is kind of very straightforward, correct? I'm saying I have 25 students, those are freshman, sophomore, or junior. I'm saying I have at least 9 of either. And can you prove it to me? So think about the worst case scenario. How many freshmen is safe for me to have? Correct, I already see it. So it's safe for me to have 8 freshmen, correct? It's safe for me to have 8 seniors, and it's safe for me to have 8 juniors. After that, any student I add is either going to bring one of my 8s to the 9, correct? But this is 8 multiplied 3, which is 24. So how do we put it into a real proof? Well, to prove, assume by contradiction I have 25 students and don't have 9 of seniors, 9 of more, well, actually pretty much, and don't have, and have, okay, and have less than, let's delete the don't. Come on. And have less than 9 of each. That means I have at most 8 freshmen, 8 sophomore, and 8 juniors. Hence, I have 24 students at most, correct? Contradiction. So this is an official, nicely written proof of how these things work. That makes sense? So I could have rephrased my original problem over here also to say, assume I have 25 students in class, prove I have at least 3 freshmen or 19 sophomore or 5 junior. And then you would have used the same thing we did, and using contradiction proved me it's impossible. Okay? And guess what? It's kind of still pigeonhole principle in a general way, correct? Because we're kind of saying, if I have more than that, then I have to have more than I have. Okay, beautiful. So section 6.3 is going to talk about permutations. And combinations. So now I want you, remember how we talked about sets, and you were supposed to remember keywords for the sets. What were the keywords for the sets? What type of elements do I have in the sets? Unordered, unique, correct. What was about sequence? Sequence was ordered, correct? Okay, good. So similarly in here, for permutation and combination, the difference is in how we defined it, and there are keywords which will help you to remember which one you need to use, okay? So permutation, your key is order matters. So that's your logo for permutation. The order matters. So let's look about permutation. Assume I have 1, 2, and 3. 3 numbers, 1, 2, and 3. I can reorder them. Agreed? I can put them in a different order. I can, for example, say it's 2, 3, 1, correct? I change the order of my number. This is permutation. So when you use the same elements, but you change the order, it's a permutation. Now, how many permutations can I have? So P and R is defined to be n multiply n minus 1 multiply n minus 2 multiply n minus r plus 1, which is the same as n factorial over n minus r factorial. This is called R permutation of set with n distinct elements. How is it useful? So pretty much it lets me know how many different permutations can I have. Sometimes I want to permute the whole set. Sometimes I just need to permute part of the set. Sometimes it doesn't even sound like permutation, but it is. So here is an example. In class, we have 30 students. I need to pick CS club president, vice president, accountant, and secretary. And maybe it's not a class, maybe it's a club, okay? In club, I have 30 students. Maybe it makes more sense. And I need to pick club president, vice president, accountant, and secretary. In how many ways can I do it? And they cannot share the position, correct? The same person cannot be president and vice president. So here are my 30 students. They are standing in front of me. In how many ways can I pick a president out of those 30 students? I just need one person. I have 30 in front of me. I have 30 options, correct? Now I grabbed my president. He stands near me. I need vice president. And how many ways can I pick my vice president? In 29. What about accountant? 28. And what about secretary? 27. This is where we need to decide, are we using product rule or summation rule. Now, in this case, we need product. Why? Well, let's see. If I'm going to have, for example, like A, B, C, and D, and I want to pick president, the president can be either A or B or C or D, correct? If I pick A, and I'm only going to pick 2, and I'm going to now pick secretary, yes, president and secretary. I can have a combination AB or AC or AD. Do you agree? So for my very first pick, I still have 3 options, correct? After I picked 1, I still have 3 options left, correct? So it's going to be 3 here for each one. So actually, I have 4 ways of picking the first one, 3 ways of picking another one, and this way is going to be multiplied by it. Do you see? This is the product rule. So now let's look about what's that. Well, this is a permutation. I have 30 people I'm picking from, and I need to pick 4. So actually, mathematically, this is 30 factorial over 26 factorial. This is what it is. And just to remind you, n factorial is n multiply n minus 1 multiply n minus 2, going all the way down to 1. This is what n factorial is. So pretty much in here, I used permutation of 30 and I got 4 out. This is you're doing permutation when order matters, when I pick a committee and the members cannot be the same. Now, another option, how many permutations? Of A, B, C, D, E, F, G, H contain A, B, C. This one is an interesting. So let's look at some good permutations. So permutation, when I'm going to have any permutation with stars with ABC is going to be good, correct? Then I can permute those things the way I want. It's going to be good. I can start with D and then do ABC and then 5 more out here, correct? And any permutation. I can like put something here and some things here. Generally, if you think about it, what is my ABC? I cannot separate them, correct? So I look at them like they're one block, correct? And if I put A in, I must put B and C directly after. Do you agree? Like there is no way. And I actually never can pick B or C, correct? That pick is not impossible. So how many such permutations do I have? So let's see how many letters besides ABC I have. So I have 1, 2, 3, 4, 5, correct? And I can put them in permutation, like pretty much at 5 factorial, correct? This is how I can put them because I need to permute all of R with 5. So permutation of 5 with 5 is going to be just 5 factorial, correct? But that's not exactly the problem, correct? Because I also can put this thing someplace, correct? So how many really things I have to permute? So I'm permuting those 5 letters, and I also can permute ABC, correct? I need to put it, but I'm going to look at it as it is one element. So I'm going to say this is my number 6. Because when I put A, I put B and C. I literally look at it as being one letter. Does it make sense? I kind of say, this is my extra element. This is my one more letter. So this is not an answer, correct? This is an answer on how many. This is good. This is how many permutations of D, E, F, G, H we have, correct? But in our case, we also have A, B, C. So the answer to the question is permute 6. So it has to include all the letters, but as soon as I put in A, as soon as I decide where A goes, I directly put BC after it. So for me, ABC comes like one letter. Okay. So this is how permutation works. Now let's talk about combination. This is where order doesn't matter. The combination is C and R. So permutation is P and R, combination is C and R, and it's equivalent into n factorial over n minus r factorial, which is exactly what permutation was. But we also divided by r factorial because we're not interested in the order inside this group. This is called and denoted like that, and it's called n choose R. So we are choosing R elements from N. And it's called N choose R. Here is an example. I'm going to start playing cards. How many cards do we have? Play cards. Okay, in this case, we're going to have 52 cards. This is a big question. So in this case, assume I have 52 cards in front of me. I'm going to pick the first one. Then I have 52 options. Then I'm going to pick the second one, which is going to be 51 options. Then I'm going to pick the next one, which is going to be 50 options. So now I have like 3 cards. I need one more, which is 49. Here we go. I have all 4. But in this case, the order in which I picked the cards is important. However, for my hand, is it matter? So assume my first card was ace of, I don't know, clubs, and my second card was 6 of clubs. Is it matter if I first get ace and then the 6, or if I first get 6 and then the ace? Is it really matter for like what hand I got, or is it the still hand of the same 2 cards? My hand is the same, correct? So it didn't really matter in which order I picked them, but I counted it differently. So the fact is, this is where my R comes in place. It says, okay, so in how many ways could I have picked those 4? I could have picked ace first and then club second, 6 second, or I can put 6 first and then a second. So I had two options for it, correct? Now, if I'm dragging 3 cards, and how many different permutations and how many different ways I can drag. So I can do like I picked card 1, 2, 3, and 4, correct? In how many different ways and how many different orders could I pick the same 1, 2, and 3, and 4? Well, it could have been that I first got 3, 4, and then 3, and then 1, and then 2, correct? So in how many ways could I have done it? Well, actually, it's a 4 factorial ways, correct? So this is where my R factorial comes from. It says, I do not care about all of those different permutations. They will give me the same hand. So in this case, what really matters is we are trying to choose 4 cards out of 52. And this is the answer. The other way to write it is choose 52. No, choose 52 4. And the value of it is Z. And I'm not going to calculate it. Now, when you are going to give me your answers, I really want to see this and that. Now you can use calculator, simple calculator to like actually calculate the number, but I'm going to see if you actually got all the different combinations right. Let's do another one. So how many 10-bit strings contain exactly 4 ones? So I have 10 spaces. And I want a B string which has exactly 4 ones. So now let's play with the thought of it. What I really need to do is I need to place my 4 ones. After I place the 4 ones in here, yes, after I find the placing for ones, everything else must be 0. Do you agree? So after I put those 4 ones, there is nothing for me to do. My combinations are done. So the question is actually equivalent to to asking in how many ways can I put 4 ones into 10 places, correct? So how can I choose the place for my 4 ones, correct? How can I find a place for my 4 ones when I have 10 spaces? Now, it's also important to remember that in this case, it doesn't matter for me if I'm going to put first one here, then one here, then one here, and then one here. Or if I'm going to first put one here, then one here, then one here, then one here, correct? The order in which I put it in there is not really important. So what does it mean? Well, what it means is I'm choosing a place, correct? So I need to choose place for my 4 ones out of 10. So this is going to be my answer, which is 10 factorial over 4 factorial over 6 factorial. And if you calculate it, this one is 6 factorial, multiply 7, multiply 8, multiply 9, multiply 10. This is 4 factorial, this is 6 factorial. I can cancel those two. So 7, 8, 9, 10. I'm just showing you how generally you can easily simplify the factorials. And then you have 2, 3, 4 here. 2 and 4 is 8. 3 and 9 is 3. So I am going to get 210 as my answer. And now I'm going to change my mind. 10-bit string. And my question is at most 4 ones. So this one is much more complicated because now what are my possibilities? This is where we start breaking it into, remember my summation, product, division, and subtraction rules. Now I can start thinking, can I break it into the cases? And am I going to need to add cases or multiply cases? Can I separate it into different buckets? So what does it mean to have at most 4 ones? So how many ones are allowed? What cases do I have? And I have a winner. Pakshal, you are the most correct one. So no ones. One, 2 ones, 3 ones, and 4 ones. Correct? This is my options. So in how many ways can I have no ones at all? I have 10 spaces. I do not allow ones at all. So this one is just one option, correct? Now, in how many ways can I just have one? 10 is correct. And some of you might check it, but pretty much what I'm doing is I'm choosing 1, correct? So this is equivalent to choosing 1 out of 10. And if you think about it, it's 10 factorial over 9 factorial, which is really 10, okay? So what about 2 ones? Well, this is choose 10, 2. This is choose 10, 3, and this is choose 10, 4. Guess what? I'm not going to waste time on trying to calculate them. I'm going to write an answer using the chooses. And this is also the type of answer. Calculating the final number, especially on homeworks, when you have your calculator, is important, so do it. But again, quizzes, tests, everything. I really want to see what you know how to get there. I really want to see your process. I really want to see what exactly did you pick? How did you come up with this number? I do not want final answer. So those things will be a must. So in how many ways can I do it? So here is the question. Do I multiply those options or is it a separate case? So is it a product or is it a sum? Okay. So let's see when it's product and let's see when it's sum. Product is when I pick something and the next case is portion of my original case. That means I kind of say I'm going to pick one CS major and one math major after. But the way I pick CS major and the way I pick math major is going to be related because I next need to pair them. So it can be this CS and this math, this CS and this math, this CS, still the same CS, and another math. So I need to multiply them. In this case, those do not connect it in any way, correct? You cannot have no ones and 4 ones at the same time. Those cases are totally separated. So it's pretty much, I can do it either this way or this way or this way. When you have the or as your connection, you need to add. So the answer is, oops, sorry. The answer is 1. Oh. 1 plus, sorry, I don't know my 1 plus C10, 1 plus C10, 2. Plus C10, 3 plus C10, 4 is my answer. So homework from section 6.3 is 8, 10, 14, 18, 20, 22 AC. This is your homework. Take a quick picture if you want it. So it's 8, 10, 14, 18, 20, 22 AC. And we are starting the section of binomials. So the binomial theorem n is bigger than 0, n is an integer. Let's look at x plus y to the power n. When we have x plus 2 squared, we can open it up and we're going to have x squared, correct, plus 2x plus 1. So pretty much you're going to have, if it's going to be x plus y squared, it's going to be x squared plus 2xy plus y squared, correct? So you're going to have different versions of what power x is going to be in and what power y is going to be in. And the question is, how do we open all those parentheses and how do we know what coefficients we have it? So the binomial theorem says this thing is equivalent to summation of j going from 0 to n when we choose j from n and x is to the power n minus j and y is to the power j. So this is literally saying it's 0n x to the power n plus 1n x to the power n minus 1y plus, keep on going, n minus 1 x, y, and oops. N minus 1 plus n out of x, y, n. So this is what it gives us. This is just a formula, and you can kind of use it. Can you guess how exactly I can prove something like this? What type of proof will I need to use in order to prove this? Yes, proof by induction is going to be what we will need, but guess what? I'm not going to do it. Instead, I'm going to teach you why is it useful? Like, how do we use it? Why is it a cool theorem? So here is an example. I want to find that without opening my parentheses. So that means the first one is going to be 3 choose 0 x cubed plus 1 choose 3 choose 1 x squared y plus 2 choose 3 xy squared plus 3 choose 3 y cubed, which is going to be x cubed plus 3x squared y plus 3xy squared plus y cubed. Now, when you do choose of n, this one is always 1. And you can play with it, but they will cancel out. So it's just 1. So there are a couple of like common things. If you have this thing, it's just n. So this is how I easily and quickly, literally figured out those computations. Okay. Now let's do another one. What is the coefficient of x to the power 14, y to the power 10 in x plus y to the power 24? So now I'm not interested in everything, correct? I'm just interested in finding one coefficient. So check first that I'm going to mark it with this. Plus z equivalent to z. If it's not equivalent, this term is not part of it. Because if you think about it, in this example, I do not have things like x cubed multiply y, correct? I do not have things like x squared multiply y squared, correct? If you look at it, my powers here, if I add them together, they're always going to be equivalent to n, correct? Because n minus j plus j is always going to be n. So this is a must. So this is one thing to check my problem is correct. Okay? So 14 plus 10 is 24. Looks good. So this is term in it. Now, let's check who is my j in this case, correct? So look, j is always what's on y, correct? So in this case, come on. 10 is j. And n is 24. So now I can just plug it into my why is it not writing? And my n is 24. So now I can use the formula and I know the coefficient is going to be j over n, but I always want to write it. So it's going to be j over n, x n minus j, 1j. So I will have 10, 24, x to the power 14, y to the power 13. Coefficient in this case is 10, 24. To remind you, by definition, coefficient is number. So if in my case, I would have gotten something like x plus 3 to the power 10, and what is coefficient of x to the power, I don't know, 5? In this case, I would have gotten 5 choose 10, x to the power 5, 3 to the power 5. So what would be my coefficient in this case for x5? My coefficient is going to be all the numbers. So the number is going to be z. On this note, we are done for today. We will talk a little bit more about binomials next time. Good luck with discussion.